All right, welcome back to the deep dive. Today we're diving into the world of weight and balance in aircraft,
Yeah.
and specifically how it all comes down to a really kind of simple principle, the law of the lever.
Yep.
This deep dive is going to use the Weight and Balance Handbook to guide our exploration.
Yeah.
And we're going to try and extract the core principles of this and really dig into how they impact the real world of aviation.
Exactly. I mean, it's, you know, what seems like all this complex stuff, the calculations about
Yeah.
weight and balance for aircraft,
Yeah.
really boils down to a pretty simple, think of a seesaw, right?
No, yeah.
That's the basic concept.
So just like a seesaw, there are limits.
Right.
Like you can't just put infinite weight on either side.
Exactly.
But
So,
you've got to have two things within limits to make sure you can fly.
yeah.
First, the total weight can't be more than what the aircraft is certified for.
Yeah.
And crucially, the center of gravity, or CG, that has to fall within a specific range. Yeah, so we've got these two limits, weight and CG,
Right.
and both of them matter.
Absolutely. And if you mess either of those up,
Mm-hmm.
you're going to have problems.
Yeah.
Stability, control,
Yeah, huge problem.
huge problems. It's not good.
Okay, so let's start by defining some terms here because we're throwing around arm and moments
Yeah.
and datum. Let's start with arm. What does arm even mean when we're talking about an aircraft?
So the arm is basically the horizontal distance, usually measured in inches, between the center of gravity of something on the aircraft
Okay,
and a reference point that we call the datum.
the datum.
Right. Now, this
Yeah.
datum
Yeah,
is an imaginary vertical plane.
got it.
And it's not like a fixed thing. It depends on the aircraft manufacturer.
Ah,
So some of them might put this datum at the very front of the aircraft, like right at the nose,
oh, interesting.
which is really interesting because then all the arm measurements are positive.
Ah,
And that kind of simplifies things.
yeah. So it's just like setting the 0 point, essentially.
Exactly. It's like
Yeah.
it's like setting the 0 point so you don't get
Yeah.
negative signs and messing up your calculations.
Yeah, fewer opportunities to mess up.
Yeah. Fewer opportunities
Yeah.
to mess up. Exactly.
Awesome. So datum imaginary line, but super important, right? It's like the baseline for everything.
It's like the universal starting line for all these measurements.
Okay, cool. Next up, moment. When I hear moment, I think about like force, some kind of force.
That's right. So a moment is basically a rotational tendency, right?
Okay.
You calculate it by taking the weight of an item, which is in pounds,
Pounds.
and multiplying that by its arm, which is in inches.
Okay.
So you end up with pound inches
Mountains.
or pound in.
Got it.
And just like arms, moments can be positive or negative depending on which side of the datum
Oh,
the
but-
weight is situated.
So it all goes back to that datum, that imaginary line.
Exactly. The datum's kind of like our anchor for all of this.
Yeah.
It's our starting point.
Okay, and then the center of gravity, or CG. This one seems kind of self-explanatory, right? It's the point where the plane would balance, basically.
Yeah, you got it. It's the point where if you could somehow suspend the aircraft,
Yeah.
it would balance perfectly.
Yeah. So how does all of this
Right.
tie back to that idea of a lever, the law of the lever?
Well, the law of the lever basically states that
Yeah.
a lever is balanced when the weight on one side of the fulcrum, so think of like the pivot point,
Yeah.
right,
Yeah.
multiplied by its distance from that fulcrum
Okay.
equals the weight on the other side,
Yeah.
multiplied by its distance.
Got it.
So in the context of an airplane, the CG is that fulcrum.
Okay. So the CG is the fulcrum.
Exactly.
And so you're saying that in order for the plane to be balanced, all the forces on one side of the CG
Yep.
have to equal the forces on the other side.
Yeah, so basically you got to have like the forces that are trying to rotate the aircraft nose up. Those have to be equal to the forces that are trying to rotate it nose down.
I see.
And when those are equal, that's when you have balance.
Gotcha. Okay. So that's the concept.
Right.
But how do we actually figure out like where the CG is located?
Right.
The handbook kind of walks through a process,
It does.
a 4-step process to actually calculate this.
It does. So the first thing you got to do is for every single item that's on the aircraft,
Yeah,
or in our analogy, the lever, you got to measure its arm, which is that horizontal distance from the datum.
Yeah.
Now remember,
Yeah.
if it's in front of the datum, that's a negative arm.
Okay. Got it.
If it's after the datum, it's a positive arm.
Makes sense.
Okay.
Yeah.
Second, you calculate the moment for each weight, and you do that by just multiplying its weight by its arm.
Okay.
Simple multiplication.
Got it.
Third step, you add up all the individual weights
Oh.
to get the total weight, and then you add up all the individual moments to get the total moment.
Got it.
And then the final step,
Okay.
you divide that total moment by the total weight.
Right.
And what you get
Yeah.
is the location of the balance point, the CG,
Yeah.
relative to the datum.
Okay, that makes sense.
Right.
So in these like simplified examples that we're talking about, we're really just looking at the added weights.
That's right.
And not the weight of the lever
That's
itself.
exactly.
Okay, cool.
Yeah.
So let's go to a concrete example. Figure 2.1 in the handbook shows us weight A at 100 pounds
Okay.
with an arm of negative 50 inches
Right.
and weight B at 200 pounds
Right.
with an arm of positive 25 inches.
Right.
So what are the moments in that scenario?
So for weight A, you multiply 100 pounds by negative 50 inches, and you get a moment of negative 5,000 pound-inches.
Okay.
And for weight B, you multiply 200 pounds by positive 25 inches, and you get a moment of positive 5,000 pound-inches.
Okay.
And if you look at figure 2.2 and you add those together, you get 0.
0, so it's balanced.
It's balanced, exactly.
Huh.
It's like that seesaw where, nobody's going up or down.
Right, right.
Everyone's just perfectly level.
Okay.
Now, the handbook points out, of course, that if you change the weight of either object or its position, which changes the arm,
Right.
then that CG is going to shift, and it won't be balanced anymore.
Okay, so that makes sense when it's just like two weights and the balance point seems pretty obvious.
Right.
But what happens if the datum, that reference point, isn't right there between the two weights?
Right.
Like what if it's figure 2.3 kind of shows this, where it's off the lever completely?
Yeah, so.
How does that affect the calculation?
So it doesn't really change anything fundamentally.
Okay.
You're still measuring from that datum. You're still calculating the arm based on that chosen point.
Okay.
So let's look at the example in figure 2.4.
Okay.
You got weight A, 100 pounds at 50 inches. Weight B, 100 pounds at 90 inches.
Okay.
And weight C, 200 pounds at 150 inches.
Got it.
So first you got to calculate the individual moments, right?
Okay.
So for A, it's 5,000 pound-inches.
Yeah.
B, 9,000 pound-inches.
Okay.
And C, it's way out there. It's 30,000 pound-inches.
Okay, big moment for C.
Big moment for C.
Got it.
Now, total weight, just add those up. 100 plus 200, 400 pounds.
Okay.
And then sum the moments. 5,000 plus 9,000 plus 30,000.
Okay.
That's 44,000 pound-inches.
Okay.
So to find that CG, you divide 44,000 by 400.
Okay.
And you get 110 inches.
110 inches.
So even though the datum wasn't right under one of the weights,
Yeah.
it's 110 inches away from that initial datum point.
Gotcha.
That's where the CG is.
Okay, so how do we know that 110 inches is really the right balance point? The handbook talks about shifting the datum.
It does.
Like as a way to prove this, and that's shown in figures 2.5 and 2.6.
Right, right. So to prove it, you kind of just imagine moving that datum to that calculated point.
Okay.
So in this case, 110 inches to the right.
Okay.
And then you recalculate all the arms of the weights, right?
Yeah.
So weight A was at 50 inches, but now it's at negative 60
Okay.
because it's 60 inches to the left of this new datum.
Yeah. Okay.
B was at 90, now it's at negative 20.
Okay.
And C was at 150, now it's at positive 40.
Got it.
And then you just redo the moment.
Okay.
A is negative 6,000, B is negative 2,000, and C is positive 8,000.
Got it.
And as you can see in figure 2.6,
Yeah.
when you add those all up, you get 0,
0 again.
0 again.
So it's still balanced.
It's still balanced.
Yeah.
So the takeaway here is that the datum is
Yeah.
kind of arbitrary.
Okay.
It's just a reference.
As long as you're consistent.
As long as you're consistent,
Yeah.
the CG relative to those weights will always be the same.
Okay, that makes sense.
Yeah.
So the handbook also touches on some other scenarios
Yeah.
where the datum, like maybe it lines up with one of the weights,
Right.
or maybe it's even further to the left.
Yep.
And this is shown in figures 2.7 through 2.10.
Yeah.
Is the process still the same? Does it still work out?
It absolutely does. No
Okay.
matter where you put the datum, whether it lines up with a weight
Yeah.
or it's way off to the side,
Oh,
it's
wow.
always going to work out.
Okay.
The key is to be consistent
Consistent.
with your measurements.
Got it.
Always measure from that same reference point.
Yeah.
And then you can do that verification like
Yeah.
you were talking about.
Yeah.
Shift the datum
Yeah.
to your calculated CG, and you'll see those moments add up to 0
Every time.
every time.
Okay, so that's really interesting.
Right. It's a pretty powerful concept.
Yeah, it's really cool.
No matter where you put that reference point, it works out.
It always works out. Okay, so this is all theory, right?
Yeah.
Like, where does this actually come into play
Right.
in the real world? Like, how do we actually shift the balance point of an aircraft, the CG, by moving weight around? And figure 211 shows this lever again
Yeah.
with 3 weights on it.
Right.
And it's balanced at 72 inches from weight A.
All right.
So how do we figure out how to move like weight B to get the CG where we want it?
So this is where it really gets practical, right?
Yeah.
Because now you're actually thinking about moving things around.
Yeah.
So in figure 211, you got this lever.
Right.
It's balanced, 72 inches from weight A.
Got it.
Now, let's say we want to balance it right at the center of the lever,
Okay.
which is 50 inches from weight A.
Okay.
So how do we do that? Well, if you look in figure 212,
Yeah.
it shows you that the combined moment created by weight A and weight C
Yeah.
around that new balance point
Yeah.
is 5,000 pound-inches.
5,000 pound-inches.
Right.
Yeah.
Now, to balance it, the total moment has got to be 0.
Right.
So weight B needs to create a moment of negative 5,000 pound-inches.
Okay. So we know the moment we need, but how do we actually know where to position it?
So you got to use the moment equation in reverse.
Okay.
Right. So we know
Yeah.
moment equals weight times arm.
Yeah.
So to find the arm, you just divide moment by weight.
Got it.
So in this case, it's negative 5,000 pound-inches
Okay.
divided by 200 pounds,
Mm-hmm.
and you get negative 25 inches.
Okay.
So that means weight B
Yeah.
needs to be 25 inches to the left of that new balance point,
Okay. So to the left.
to the left.
Got it.
And you can see that in figures 213 and 214.
Yeah.
They show you where that new position would be.
Okay.
If you calculate the total moment
Yeah.
with B in that new spot,
Yeah.
it comes out to 0.
Balance.
Balanced.
All right. That's really cool.
Right. It shows you how moving things around actually changes the balance.
Yeah. It's super practical.
Yeah, it's very practical.
So the handbook also presents some like weight and balance equations that seem like they could be really helpful.
Yeah, these equations are basically just ways to calculate different things more quickly.
Okay.
So you can calculate like how much weight you need to shift,
Oh,
or the total weight of the aircraft,
Yeah.
or the change in CG
yeah.
that you'll get from shifting weight,
Yeah.
or even how far you need to move a weight
Okay.
to get a certain CG change.
Yeah, that's really useful.
Yeah, so one of the most common equations
Okay.
is weight to be shifted equals
Yeah.
change in CG
Time is
times total weight
divided by.
divided by the distance.
Okay.
The weight is shifted.
Got it.
And you can rearrange that equation to solve for any of those things.
Okay. So let's go back to that previous example.
Sure.
With the CG at 72 inches.
Okay.
And we wanted to move it to 50 inches.
Right.
How would we use those formulas
Okay.
to actually figure out how to shift weight B?
So in that case, the total weight was 500 pounds.
Okay.
The change in CG was negative 22 inches.
Okay.
Because we're going from 72 to 50. And the weight we're shifting is 200 pounds.
Okay.
So if you plug all that into the equation
Yeah.
to solve for the distance, you get negative 55 inches.
Okay.
And that negative just means it's moving to the left,
Got it.
which is what we found before.
Okay. And so what if we knew the distance?
Yeah.
Like, let's say we knew that weight B
Yeah.
got shifted by 55 inches.
Okay.
How could we quickly figure out how much the CG
You would just
would
change.
a different variation of that formula?
Okay.
So it would be change in CG
Yeah.
equals weight shifted times distance shifted
Okay.
divided by total weight.
Got it.
And if you plug those numbers in, you get 22 inches.
22 inches. Okay.
So again,
All lines up.
it all lines up.
Yeah.
Shifting that weight by 55 inches changes the CG by 22 inches.
Okay. Cool.
So, once you understand the basic idea,
yeah.
you can use these formulas
Yeah.
to figure out
As shortcuts.
all sorts of stuff.
Yeah. Okay. Yeah.
So let's talk about something that seems very specific to aircraft.
Sure.
The mean aerodynamic chord, or MAC.
Yeah.
What in the world is that?
So the mean aerodynamic chord, or MAC,
Yeah.
it's basically like the average width of the wing.
Okay.
If the wing was a rectangle,
Yeah.
it would just be the length of the chord.
Yeah.
But most wings aren't rectangles, right?
Right.
They taper.
They do.
So the MAC is like a way to capture that average. And it's important because the location of the CG
Yeah.
is often expressed as a percentage of MAC.
As a percentage of the MAC. Okay.
So instead of saying the CG is, 150 inches
Yeah.
after the datum,
Yeah.
you might say it's at 25% MAC.
25% MAC. Okay.
And to actually use that, you got to know where the leading edge of the MAC is
Yeah.
relative to the datum.
Got it.
But it's a useful way to think about
Okay.
the CG in relation to the wing.
Yeah. So it's accounting for the fact that the wing is tapered
Exactly. It's like saying,
Yeah.
how much of the wing
Yeah.
is in front of the CG
Got it.
and how much is behind it.
Okay, cool.
Yeah.
And that brings us to CG limits. We're like, why do we even care about
Yeah, so
other CG groups?
CG limits are
Yeah.
basically the forwardmost and aftmost
Yeah.
locations that the CG can be
Okay.
while you're flying.
Okay.
And the area in between those
Yeah.
is the CG range.
The CG range.
Right. And these
Okay.
are super important.
Yeah. I imagine they're really important.
They are, because
Yeah.
if the CG is too far forward,
Yeah.
the plane's going to be nose heavy, and it's going to be hard to control,
Yeah.
especially during takeoff and landing.
Okay.
And if the CG is too far aft,
Yeah.
the plane can become really unstable,
Yeah.
which is obviously not good.
Not good at all.
Not good at all.
Okay, so who decides where these CG limits are?
So the aircraft manufacturer,
Okay.
they figure those out during the design process.
Got it.
And they're very carefully chosen
Yeah.
to make sure the plane is safe
Yeah.
to fly.
Okay. That makes sense.
Yeah.
So, all this talk about theory and calculations,
Oh, yeah.
it's really interesting. But in the real world,
Right.
where do you actually find this information?
So there's two main sources.
Okay.
You got the FAA
Okay.
and you got the aircraft manufacturer.
Okay, so let's start with the FAA. What do they give us?
So the FAA's main source of info
Yeah.
is the type certificate data sheet,
The TCDS.
or TCDS.
Yeah.
Now, for older aircraft
Yes.
certified before 1958, it's called the aircraft specifications.
Okay.
But basically, these are the official documents
Yeah.
that tell you all about the aircraft.
Okay.
Its design, performance limitations.
Got it.
And that includes weight and balance data.
Okay.
And the cool thing is,
Yeah.
you can find all of this on the FAA's website.
So it's publicly available.
Yeah, it's publicly available.
It's awesome.
So anyone can look it up.
Cool.
And, mechanics, they got to make sure the aircraft meets those PCDS specs.
Yeah, during those annual inspections and things. So
Okay.
cool.
Yeah.
So what kind of stuff
Right.
can you actually find in the TCDS?
So the TCDS will tell you
Yeah.
the approved CG limits,
Okay.
the maximum weights
Okay.
for different things like takeoff, landing, and just sitting on the ramp.
Yeah.
It'll tell you about the seats,
Okay.
like how many there are,
Yeah.
and where they're located.
Okay.
Same thing for the baggage compartments.
Got it.
The fuel tanks,
Yeah.
the oil,
Yeah.
it's all in there.
Okay, cool.
Yeah.
So the handbook gives us an example of a TCDS excerpt.
Right.
And that's for a Cirrus SR-20, and that's shown in figure 215.
Yeah.
One thing that's interesting is that it seems like the CG range
Yeah.
isn't just fixed numbers.
Right.
It can actually change
It can.
depending on the serial number.
Yeah. That's pretty common,
Okay.
especially for aircraft that have been, updated over time.
Right.
So in the SR-20 example,
Yeah.
you can see that the forward and aft CG limits,
Yeah.
they change for different serial numbers.
Okay.
Like for planes with serial numbers from 1005 to 1147,
Yeah.
the forward CG limit,
Yeah.
it's not just one number.
Yeah.
It actually changes
Yeah.
based on the weight.
Okay, so it depends on the weight too.
Yeah, so at 2,110 pounds,
Yeah.
it's 138.7 inches
Yeah.
after the datum.
Okay.
But at 2,900 pounds,
Yeah.
it's 143 inches.
Okay, so it changes. Yeah.
Yeah, it's not just one fixed number.
That's really interesting.
It is.
Okay, cool.
And you'll also notice that for the empty weight CG range,
Yeah.
it says none.
A none. Yeah, what does that mean?
That basically means that because of how the plane is built,
Right.
like where the seats and stuff are,
Yeah.
it's pretty much impossible
Okay.
to load the plane.
Yeah.
So that the CG is outside the limits.
Okay, so it's kind of like built in.
Yeah, it's like built-in safety.
Yeah, that's really cool.
Yeah.
Okay, so the TCDS also gives us the maximum takeoff
Right.
and landing weights.
It does.
And again, those can vary.
They
But
can,
yeah.
by the SR-20s,
Yeah.
with serial numbers 1005 to 1147,
Yeah.
the max takeoff and landing weight is 2,900 pounds.
Okay.
But then for later models,
Yeah.
like starting with serial number 1148,
Yeah.
the takeoff weight goes up to 3,000 pounds.
Okay.
And then even later,
Yeah.
like 2016, and
Yeah.
both the takeoff
Yeah.
and landing weight
Yeah.
go into 3,050.
3050. Okay.
So it's really important.
Yeah.
Always check the specific TCDS
Yeah. For your specific aircraft.
for your specific aircraft.
Okay, got it.
Because those numbers can change.
Okay. What about stuff like
Right.
the seats,
Yeah.
baggage, fuel, all that stuff?
Yeah, the TCDS tells you where all that's located too.
Okay.
So for the SR-20, it's got 4 seats.
Okay.
2 of them are at 143.5 inches aft to the datum,
Okay.
and the other 2 are at 180 inches.
Got it.
The baggage can weigh up to 130 pounds,
Okay.
and its arm is 208 inches.
Got it.
Fuel, total capacity, is 60.5 gallons
Okay.
at 153.75 inches.
Okay.
And then oil, 8 quarts at 76.2 inches.
Got it. So it's all laid out in the TCDS.
All right there.
Awesome. So that's the FAA. What about the manufacturer? What did they give us?
So the manufacturer, they give you a bunch of documents too.
Okay.
One of the most important is the weight.